All right. Right. So as I was telling you that vectors is a very important subsection of physics where we understand how to deal with certain physical quantities which have both magnitude and direction. And what I mean by saying that we learn to deal with them is we learn to do algebra with them. Okay, so how to add vector quantities, how to subtract vector quantities, how to apply the concept of product to vector quantities to get other significant type of calculations. So that becomes very much part and parcel of everyday physics, because most of the quantities, many of the quantities we deal with in physics are actually vector quantities. So let's start with understanding what are vectors exactly. So let's look at the definition of a vector. Okay. So I will in fact understand the definition of a vector by first relating you with an example. So suppose we have a situation like this, that I'm observing now, since we had been talking about motion in the last couple of lectures. So let's continue in that vein. Okay. So suppose I say that a body or a person or whatever, okay, moves such that it has, or you can say it covers. So we say that the body covers a distance, let's say d1 of 12 kilometers and displacement, let's say s1 of 8 kilometers. Just a moment, I have few more people in the waiting room. Yeah. So let's understand this example again. So it says that it has a distance, it covers a distance of so much, whereas it covers a displacement of 8 kilometers. So you understand that distance can always be larger than displacement. So that's why this one is 12 kilometers, whereas the displacement is 8 kilometers from, let us say, 12 to 12:45 p.m. Okay. And then again, followed by again distance d2 of, let us say, 15 kilometers. This again I'm talking about distance, and displacement s2 of, let us say, 6 kilometers from 12:45 to 2 p.m. let's say. Okay. Now having said this, now what I'm trying to find out over here, the question I'm asking is that what is going to be the net distance covered and what is going to be the net displacement in the entire interval from 12 to 2. So now we want to find out the net distance d from 12 to 2 p.m. And along with that, I also want to find out the net displacement S from 12 to 2. So now the moment you visualize this problem, you realize that, okay, so I'm just going to minimize this a little so you can see the whole thing. Right. So the moment you look at this problem and you visualize it in terms of what you know as the definition of distance and displacement. So what is distance? It is the length of path traveled. It's the actual path length that a body covers. Whereas what is displacement? It is the straight line joining the initial and the final position, or it is the shortest path from the initial and to the final position. So you realize that when you're working out this example, the second part of the question is a problem. Okay, because let me just demonstrate. So what could have happened over here is, for example, let's say this is where my body's location is, or this is where my particle's location is at 12 p.m. Okay. Now from here, let's say it starts moving like this through some kind of a path, because we don't know the path. So I'm just trying to visualize. And suppose the body reaches, let's say, here at 12:45 p.m. So the information that I have now about this right now is that this line, the line joining with this this is a straight line, which is the displacement. This displacement S1 I had given you has a magnitude of 8 kilometers. Whereas the distance traveled, which is going to be the path length over here, this distance traveled, D1, is going to be 12 kilometers. Okay. So this is the sense I can make out of the first part of the statement that I've given earlier. Okay. From the first part of the statement that I've given earlier, this is this exact sense I can make out, that it covers a distance of 12 kilometers, but a displacement of 8 kilometers from 12 to 12:45 p.m. So just following the information, if I try to visualize it, this is the kind of diagram I can think about. Now let's come to the second part of it. Okay, now the second part says that from 12:45 to 2 p.m. it covers a distance of 15 kilometers, but a displacement of 6 kilometers. So what would that look like? So let's again, continue this forward and try to visualize that. So now if we try to visualize this further, we can say that, okay, from here, let's say it goes on some kind of path like this and reaches somewhere here. And let us say this is where the particle ends up at 2 p.m. or this is where the body ends up at 2 p.m. So now what is the information that I have further? That this straight line joining my position from 12:45 to 2, that is the displacement which I've given in the second part of 6 kilometers. Okay. And the distance traveled in the second part of the journey, that is this path length, this D2 is actually equal to how much? It is that, whatever that, 15 kilometers, I think it was. Okay. But now what I'm asking you is the net distance. So the net distance is going to be nothing but the total path length. So it's going to be the sum of this. Okay, so if you just follow my cursor, it is going to be the sum of this path length here plus this path length here. So it is going to be nothing but D1 plus D2. So it is going to be 27 kilometers. Okay, so that's fine. But if I ask about the net displacement, now then that is a big question mark, because I can see in the diagram, my net displacement is not going to be 8 plus 6 at all, because net displacement will be defined as this. You can see that this thing over here is going to be my net displacement. And right now I have no information about how this is, because I don't know the relationship between this one and this one in terms of the angle. Now you can notice, for example, if the angle between the two arrows, the red and blue arrow, S1 and S2, had been 90 degrees, then this would have been the hypotenuse of a right angle triangle. So this could have been 10. But on the other hand, if this was in the same direction like this, then it could have even been 14. Or if it was exactly in the opposite direction and somewhere here, then it could have even been 2. So the thing is, we cannot calculate this from the information given. Cannot calculate. Because, why we can't calculate? Because there is no information about direction. There is no information given to us about the direction. So what, in a nutshell, what we are learning from this example is that if you look at the quantity distance, okay, it does not, part of the definition of distance does not have anything to do with direction. Distance is just path length traveled. That is why when we are adding two distances, we are just adding them by what is called scalar algebra, or we are just doing arithmetic addition. This over here is arithmetic, just like two numbers we add. But displacement, we cannot do that. Okay, we cannot add that way. By simple arithmetic. There is something to do with direction involved over here. So that is why we say that displacement is a different category of physical quantity compared to displacement. If distance is what we call a scalar quantity, because we are doing the addition according to scalar algebra or according to normal arithmetic, then displacement is something which we call a vector quantity, because for doing algebra with displacement, we need the direction of the vector. Just the magnitude is not enough. So now if I modify this question, okay, and if I modify this question and I make it like this now, that let us say, suppose if in the above question, so the same situation as above, I know that S1 is equal to 8 kilometers towards east. And additionally, I know that S2 is equal to 6 kilometers towards south, okay, then I know that I can calculate the net displacement because I've given information. I'll be able to calculate this. I'll just have to visualize the problem and I'll understand that in my new situation, if this is S1, then something like this will be S2, because we will take the standard directions like this. Suppose in my diagram, this represents north, this represents east, this represents south, and this represents west. So S1 will be like this. It will be towards the east and it will be 8 kilometers long. S2 will be like this at 90 degrees to this because it is towards south. Okay. And therefore my net displacement in this diagram will now be very well defined. It will be defined by this. So you can see that just using simple geometry, I can now predict that, okay, my net displacement, okay, at least in terms of magnitude, I can see it's going to be square root of S1 square plus S2 square. So that over here is going to be 10 kilometers because the hypotenuse of 8 and 6, all of you know, is 10. Okay. So this is now known why, because what is given to me additionally is the direction. I've given you the direction of the individual displacements. So that is playing a role over here. Okay. And the same thing if I give you some different directions now. Okay, now don't worry about the distance traveled over here because that's going to be the same. So if the path of the body was something like this, and then something like this, it doesn't matter. My distance traveled is still going to be the same. If D1 was 10 or whatever it was, yeah, I don't remember, 12 I think. So if the distance traveled here was 12 kilometers and the distance traveled in the second part was 15 kilometers, then the net distance will still be the same thing. It will be D1 plus D2. So it will be 27 kilometers. So there's no change in that. But the thing is, because I have additional information about the direction of the displacement, I can say that the net displacement is going to be the same thing. In the same question, suppose if S1 is towards east again, but now S2 is towards west. So this could also happen. So we could have a situation where the body goes from this point via some path like this, ends up somewhere here, and then second part, it comes via path something like this, and then ends up somewhere here. Okay. So you can see that S1 in this case is going to be this displacement. This is going to be my S1, which is 8 kilometers towards east. But in the same diagram, my second displacement S2 is going to come in here now. So from this point, now the displacement is back to this point. So this is my second displacement, S2, which is 6 kilometers towards west. Okay. And therefore, my net displacement now in the same diagram is going to be the line joining the absolute initial position at 12 o'clock to the final position at 2 o'clock, which is this one. So I just draw it slightly below, but you understand that basically these arrows are all overlapping. They are all along the same line. So this over here is going to be my net displacement. And you can see that, because this is where he was at 12 p.m. Then this is where he ended up at 12:45 p.m. And finally, this is where he ended up at 2 p.m. So from 12 p.m. to 2 p.m., his net displacement is just this. His net distance covered is more. It is 12 plus 15, but his net displacement is only 2 kilometers. So in this case, you can see the net displacement is in fact equal to S1 towards the east minus S2 towards the west. So it is just 2 kilometers. So you can see that the same values of displacement or the same magnitudes of displacement in both case 1 and case 2, they are 8 and 6. But in one case, because they are perpendicular to each other, so the resultant or the net is in fact becoming how much? This resultant is becoming 10 kilometers. Whereas in the second diagram, the net is only becoming 2 kilometers. This net is only 2 kilometers. So you can see that direction can have a profound influence on how the vector quantities are relating to each other, or in this case, how we are adding them with each other. That's how we are building the relationship between them. So that is, profoundly affected by the direction. Whereas in the case of distance, okay, nothing like that happens. So just, I will just zoom out of this a bit, and you can just take a look at both the cases carefully with the data given about them. So let me minimize it a little further. Okay. You can make a brief note of this too, and more importantly, because I will be giving you the class notes, so don't worry. More importantly, you make sure that you understand this case. Okay, so this is the first case. So if in the above we make this assumption that this is towards east and this towards south, then this is what the resultant looks like. Whereas on the other hand, if we assume that instead of east and south, the directions are east and west, then the net is becoming like this. So yes, I am seeing some of your answers. So Aman, you have got the first part correct. Okay, and I will tell you about reference books. Don't worry. Okay, we will have mentoring sessions, etc. also, where we will discuss about reference books. But just as a general advice to all of you right now, reference books for the moment, since markets and all are closed, you can completely rely on our module. Now, the PDF of the module which you have got, you can completely rely on that. If there is anything additional to that required in physics, for example, in my subject, I will be providing you with additional PDFs. Okay. Of course, there is a lot of things that you can go through for self-interest, and you can discuss with me separately. I'll tell you about that. But in terms of what is absolutely necessary for your course right now, that would be okay. And Ritika, to answer your question, what would be the direction of the displacement? Yes, that is a good question. So now you can see in the first case, I don't exactly know the direction. I have to work out the angle. I can see that it is somewhere towards south of east. And in the second case, you can see in this case, the displacement that final that we are getting is somewhere here. So it is between east and south. Okay. So now the next step for us would be, if I can calculate this angle, then I can say, if I can find out how much that theta is, then I can say that the direction is theta degrees south of east. So that is how I would express the direction. But for that, I'll have to calculate the angle. And for that, I'll have to apply trigonometry over here. Because you can see in this triangle, tan theta is 6 by 8, or that is 3 by 4, or 0.75. So I'll have to go back to a trigonometric table and find out that, okay, tan theta is equal to 3 by 4. So what does that mean about theta? If you do that, you will find out that the theta will in fact come out to be 37 degrees. Okay. But anyway, in this question, I'm not asking about that angle and direction. So this is not significant just now for the moment. We will come back to that angle later. Okay. So in fact, this is some of the things that we'll be discussing about. Okay. So yeah, so hope, yeah, to answer another question, if both were towards west, for example, or both were towards east, then the resultant would have just become 8 plus 6, it would have become 14. Okay. So if we had another case where this one is also towards east, this one is also towards east, then the net would have looked just like a straight line towards the west with a value of this much, with a resultant displacement of 14 kilometers in this case. Okay. So in fact, you will also realize that a combination of displacements of 8 and 6, what is the maximum value of the net which is possible? And you'll realize the answer to that, that is 14. Because the maximum value will happen when they are both in the same direction. So the resultant will actually become the sum of 8 and 6. It will become the normal arithmetic sum. It will be 14. So in no circumstances a displacement of 8 and 6 can give you a net displacement of more than 14. But there are a lot of circumstances where it can give you less than 14. And that is some of the examples that we'll be discussing. So now with this example in place, we are in a position to define exactly what is a vector quantity. So in fact, how we'll define it is like this, that all physical quantities, and we all understand that physical quantities are quantities that can be measured. So they are the quantities that we deal with in physics. A non-physical quantity would be something that we cannot measure. So that is not part of our domain of physics. So all physical quantities, based on this assessment, we divide them into two categories, okay, vectors and scalars. So scalars are the simpler of them. Scalars are quantities which are defined, or they have only magnitude. They don't have a significant direction. Okay. So there are so many examples of this. Distance was just one of them. But basically anything you think where when we are adding or subtracting, we don't take into account distance. We just add or subtract them like we would add normal numbers. So distance is an example, volume is an example, mass is an example, okay, speed is an example, okay, energy is an example, okay, so many such examples exist. Whereas vectors are quantities which are defined by both their direction and magnitude. So they are defined, or you can say they have both direction and magnitude. So until we define the direction and magnitude, the definition of the vector is not complete. Okay. So example of that is displacement, as we just saw. Okay. Another very easy example to visualize is force. If we are applying two forces along the same direction on a body, the net force becomes the sum of their magnitudes. But if we are, for example, applying the forces from opposite direction, it can even become the difference. If we are applying the forces perpendicularly, we will understand, yes, later how to calculate the sum. Velocity is another example because it's related to displacement, whereas speed is related to distance. So because distance is a scalar quantity, speed also becomes a scalar quantity. But because displacement is a vector quantity, velocity becomes a vector quantity. No, pressure is actually a scalar quantity, to answer your question. And electric current is also something somebody has asked, and it's an interesting question. So I'll explore it in just a moment. You will answer the question yourself whether electric current is vector or scalar. So these are some of the examples. More abstract examples would be things like electric field, which is the force field created by charge, or gravitational field, which is the force field created by gravitational mass, or there is acceleration in kinematics. Okay, linear momentum in dynamics, because momentum is just defined as mass into velocity. So these are all examples of our vector quantities. Okay. Now, as you are just briefly going through this list, okay, let me pose an interesting question. Okay. Is electric current a vector or a scalar? Okay, and you can just send me your answers in chat. You can just send an answer as vector or scalar, or just yes or no, like that. Atharva, magnetic field is also a vector quantity. Okay. Okay, so most of you are saying scalar, okay, which is in fact correct. One or two are ambiguous about it. I even see an answer which says depends. Okay. Now the thing is, in physics we typically don't have any such thing as depends. Okay, we have to give a definite answer whether it is a scalar or vector. Okay, so let's understand this. Okay. So if I just ask myself the question, does electric current have direction? Or does it only have magnitude? Okay. So the answer to that definitely is yes. We know that electric current flows from higher potential to lower potential. We all know that. Okay, so if we connect a battery this way, the positive terminal here and the negative terminal here, we know that through the resistor, the current will be flowing from the point A to the point B. Because the point A is connected to the higher potential of the battery, the point B is connected. Whereas if I had in the same thing connected it like this, then in this case now the current would flow in this direction. It would flow from B towards A. It would flow like this now in this circuit. So in that sense, yes, you can say it has a direction. It flows from higher potential to lower potential. But does that necessarily mean it's a vector? So let's try and understand. So let us look at an example of addition of currents. Okay, let's look at that. So let's say we have a situation like this where we have connected a resistor like this now. Okay. And let us say this is creating a current I1. This is sending in a current I2. Okay. And the resultant current here becomes I. So we have the relation that I is the sum of I1 and I2. So suppose I1 is 2 amperes and I2 is 3 amperes. What can we say about I? It will always be 5 amperes. There's no doubt about it. Okay. Now consider the situation where I change the direction a little bit. Okay, so I make this second wire like this. And I make this first wire like this. Okay. So you can see I1 is coming in from a different direction. I2 is coming in from a different direction. But this net current I will still be the same. Okay, so it is I will always be equal to I1 plus I2 as what is called a scalar sum. This is how we add scalar numbers. This is how we add two volumes, or this is how we would add two masses. There's no question of this angle involved. This angle theta does not make any difference whether the angle is 180 like it is over here, or it is some general angle like an acute angle over here. It doesn't make any difference. So you can see that since current algebraically follows the rules of scalar algebra and not the rules of vector algebra, hence current, electric current I, is a scalar. Okay. So similarly, any physical quantity that we come across in future, where if for any reason we have some confusion whether we should treat that quantity as a vector or a scalar, this is a very simple test to understand whether the given quantity is scalar or vector. Just think of how you would sum or how you would add two values of that quantity, and if you're pretty sure that you can use the normal principles of scalar algebra to add them, and you don't need any information about direction to add them, then you know that it's a scalar quantity. Because on the other hand, if you realize, like in the case of displacement we did, or for example in the case of force, so let's see in the case of force what happens. So suppose we are applying two forces on a body and they are like this. In one case we are applying a force F1 of 5 newtons and a force F2 in the opposite direction of 2 newtons. Okay. In another case we are applying the force F1 and F2 in the same direction on the body. So we'll see that in this case the net force, okay, in case A, the net force will be actually 3 newtons, okay, because they are acting from opposite directions, so they'll tend to cancel each other. Whereas in case B, you can see that the net force will in fact be 7 newtons. Okay. Or if you applied them perpendicularly like this, it would be something else. Suppose I applied F1 like this and F2 like this in a different case. See over here, there would be something different altogether. So you can see that force is which kind of quantity? Force is becoming a vector quantity. Whereas electric current, we have just understood, even though in the traditional sense we can say that yes, it has direction, it flows from higher potential to lower potential. But in terms of our new definition of vectors and scalars, it falls in the category of scalars. Alright, so this is about the general understanding of what are vectors and scalars. Okay, so now that we have understood not only the definition of vectors and scalars, we have also understood that given a certain quantity, how to test, how to do a small test ourselves to understand whether it is vector or scalar. Next, we move on to what is called vector algebra. That how we actually deal with vectors quantities, how we do the various algebraic operations on them like addition, subtraction, etc. So the first part of vector algebra now is going to be what we call notation for vectors. How we notate them or how we use symbols. Or for vector operations, how we use notations. Let's understand that. Okay, so for notation, we'll understand that if we use any symbol, any alphabetical symbol with an arrow on top, the arrow represents the vector symbol. So this is read as vector E. The physical quantity that A is representing now is a vector quantity. This is what the arrow on top means. Whereas if we were to just use the symbol alone, now from now on we will understand that this is a scalar quantity. So we are talking about speed, for example, we'll write it as V because it's a scalar quantity. But But if you're talking about velocity, we'll write it as this, because this is a vector quantity. Okay. If you're talking about energy, for example, it's a scalar quantity. But if you're talking about, for example, let us say force. So from now on, force is a vector quantity. Okay. So any alphanumeric or any alphabetical symbol with an arrow on top, the arrow's direction is not important over here. The direction is always written like this. So any symbol like X with an arrow on top, it represents the vector X. It's a vector quantity. That's the notation that we use. Okay. Now the other notation that we use, which is important, is magnitude of a vector. So sometimes we also use the shorthand term modulus, or simply mod. In very short, we might call it just mod. So that is notated by this symbol. Your regular, modulus symbol in mathematics, you put the vector inside it. So this symbol now is read as magnitude of vector E, or this symbol would be read as magnitude of velocity. V. Okay, so this is just a matter of symbols. We have to develop a system of consistent symbols. So this is what we develop. Okay, so you can make a quick note of this if you like. I'll just minimize this a little. So it's very important that you understand the difference between the symbols that we use now for scalars and the symbol that we use for vectors. Okay, people. So the vector symbol and putting it between two bars, or the normal modulus symbol that we use in mathematics, but in vector algebra, that modulus symbol actually stands for magnitude. We might also call the magnitude as modulus or mod in short form, but the proper word for it is magnitude. So for example, now with this notation in mind, you will see that if I write an equation like this, that F is equal to 15 newtons. Okay, as an equation, this is now wrong. Okay. This is a technically incorrect equation. Why it is incorrect is because, see, what is happening on the left hand side, the quantity I have on the left hand side is the vector, which is force. On the right hand side, the quantity I have is only magnitude. I don't have any reference to direction. So that means it's a scalar quantity. So can I equate a vector with a scalar? No. That is why this becomes incorrect. But on the other hand, if I say that the magnitude of force is equal to 15 newtons. Okay. Now there's no problem with this. This is now technically a correct statement. Why this is a correct statement is now the left hand side is magnitude of a vector. So the magnitude of a vector is a scalar because it's just the magnitude of it. Whereas the right hand side is also just a scalar, or it's just a magnitude. So this is correct. So this is correct. Okay. Now before I give you to note this down, how would I write the proper statement involving the vector? One way of saying that statement would be, if I write F is equal to 15 newtons vertically upwards. Okay, so now there's a correct statement, because what is happening on the right hand side, I have both magnitude and direction. And I'm equating it with what kind of quantity on the left hand side? It is a vector. So I'm relating a vector with both its magnitude and direction. So hence this statement is correct. Okay. So just to understand, the technicalities of notation, the proper technique of writing notation, it's important that you understand this example. Okay. So I'll just minimize this. So you write the notation also first and then understand these two statements. Alright, people. So this is just about correct notation. Okay, next up. Yeah, the difference between the last two equations, let's go over that again. So see, the second equation which I've written, it says modulus of a vector, mod of f is 15 newtons. So it's a correct statement because I'm just saying magnitude and that is how much? 15 newtons. There is no reference to direction. Left hand side में भी मैंने क्या लिखा है? Vector का सिर्फ magnitude लिखा है. So there's no reference to direction. और right hand side में भी मैंने क्या लिखा है? Only 15 newtons. So there's no reference to direction. So I'm referring to only one thing over here, that the magnitude of the force is 15 newtons. So that's correct. Okay, but in the first equation, for example, I'm saying the force is 15 newtons. So why that is incorrect? Because force has to be defined in terms of both magnitude and direction. If I just tell you that, okay, the force is 15 newtons, I'm just giving you information about magnitude of the force, no information about direction. That means I'm not giving you the force. I'm only giving you one aspect of the force, and that is the magnitude. And that's what's happening in the second equation also. But in the second equation, the left hand side, I'm not saying it's the vector, I'm saying it's the magnitude of the vector. So it's a valid statement that the magnitude of the vector is so many units. But if I say the vector is so much, I cannot get away by just saying that the vector is so many units. I have to tell what is the direction of the vector also. So that's why your third equation comes. That your third equation, the left hand vector quantity, the right hand is telling you units along this direction. It's complete. That is why the statement is now technically correct. Okay. So of course your third statement is giving you more information than the second was giving you, because it's giving you information about both direction and magnitude. But as far as technically is concerned, both the statements are correct. There's nothing wrong with it. But the first statement, as you can see, was technically wrong, because left hand side is talking about a vector quantity and right hand side is just talking about a magnitude. So you cannot equate a vector with a magnitude. That was the problem with the first equation. Now next thing we'll see is, now we are moving on towards how to understand algebraic operations. So first of all, in that we'll see how to represent a vector not by words like we've done over here. That is, so many newtons towards vertically upwards, or the displacement was so many kilometers towards north, and all that. That becomes a little cumbersome after a while. So we find an easier way to represent vectors, and that is the geometrical method. So next, very important, we'll understand the geometrical representation of vectors. So instead of writing a line like we've done earlier, with the complete description in words and all that, how we can very smartly use geometry to represent a vector? And the answer to that is we can just draw an arrow. Because when we geometrically draw an arrow, the arrow has two very distinct features. One is the line of action along which the arrow is acting. That is, in this case, this line. and the other is the specific length of the arrow, which in this case is this length. So if you look at this length of the arrow, it can be used to define the magnitude of a vector. Whereas if you look at the direction, or what we call the line of action, along which the arrowhead is pointing. This arrowhead is pointing along a particular direction. So that direction, so a vector is represented by drawing an arrow, okay, such that the length of the arrow is directly proportional to the magnitude or mod A, and the direction of the arrowhead is equal to, or you can say is the direction of vector E. Or in better words, we can say it is what we call the line of action. So if it is a force vector, the line of action along which the force is acting is this one. If it is a displacement vector, the line of action along which the displacement is acting is this one. So this is how we use geometry to represent a vector. Okay. So for example, if I have this equation over here that I've drawn one displacement, let's say S1, okay, and it is, let us say, 10 kilometers. So that means this length over here is proportional to 10 kilometers. Now if I draw another one like this, let us say, and I tell you that this is my displacement S2, where this one's magnitude is 5 kilometers. And this angle between the line of action of this one and this one is, let us say, 30 degrees. Okay. Then what should happen? That first of all, the length of S2's arrow should be half of the length of S1's. Okay. In a proper diagram, I should actually measure this and make this exactly half. But here it's just, we are making a symbolic representation. So, so you understand what I mean by length being proportional to the magnitude. If this arrow represents 10 kilometers, then an arrow which is half its length should represent 5 kilometers. And the second thing is, you can see that S2 is at theta equal to 30 degrees angle with respect to S1. That is the other information that this is giving. Okay. So this is how these two arrows give me simple information about the two vectors S1 and S2 as I'm showing you. Okay. So just make a quick review and note of this. Okay, people, is this clear? Right. So make a note of this example. Okay. And now try out what I'm saying on a piece of pen and paper. Okay. So listen to what I'm saying carefully and work out what I'm saying. Okay. So draw vector arrows to represent the following. Okay. So try this on pen and paper. So draw vector arrows to represent the following. Okay. Vector A. Okay. Vector A equal to 15 units towards east. Okay. Vector A equal to 15 units towards east. Okay. Vector B. Okay. Vector B equal to 20 units towards south, okay, vector B equal to 20 units towards south, and vector C equal to 25 units, okay, vector C equal to 25 units at 30 degrees north of west. Okay. So I'm repeating, vector C equal to 25 units at 30 degrees north of west. Okay. So like I made a diagram for S1 and S2 over here, just make a diagram for these two and try to make as accurate as possible. You don't have to use pen, you don't have to use a protractor and scale and all that, but just try to make as accurate as possible on pen and paper with hand a diagram that represents arrows which represent these particular vectors. Just try this out, people. Okay, people, so if you finished making the diagram, just take a quick 1 or 2 minute break. Okay, I'm just refreshing my white screen till then. It's got hang. Okay, and I'll put up the question and the solution on the board. So just to repeat my question, you are supposed to draw a diagram with vector arrows to represent the following. Okay, a vector A, which is 15 units towards east, then a vector B, which is 20 units towards south, and finally a vector C, which is 25 units at 30 degrees north of west. Okay, 30 degrees north of west. So just finish doing this and take a quick 2 minute breather, and we'll continue from there.